Suppose I asked you to add the following two numbers on paper. It would take you what, like 7 seconds? But if I gave a harder version of the problem to my old laptop, a million additions in a row, with all the numbers swapped out for 100-digit monsters, it would finish all of it in about 2 seconds. So how do computers add numbers so fast? In this video, I'll explain how computers perform addition. We'll start with the basics, like how computers even represent numbers, and then work our way up to how real, modern processors actually do addition as fast as physically possible. By the end, you'll understand the elegantly simple logic at the heart of every processor ever made. Let's start with how computers even handle numbers. You already know base 10. It's the number system you've used your whole life. When you write the number 395, what you really mean is 3 times 100 plus 9 times 10 plus 5 times 1. You could also simplify the second terms like so. In base 10, each digit position represents a power of 10 and digits go from 0 to 9. But computers don't use base 10, they use base 2 or binary. The reason why is beyond the scope of this video, but it has to do with stability, among other things. Anyway, in binary, each digit position represents a power of 2, and digits only go from 0 to 1. Let's make sure that's clear. The first part of each term is the digit, which is either 0 or 1, and the second part is the associated power of 2. For position 3, we have 2 to the power of 2, for position 2, we have 2 to the power of 1, and finally, for position 1, we have 2 to the power of 0. Notice how the powers are off by 1. This is because we are counting the powers from 0. Now, let's look at addition. You should already know how to add in base 10. Basically, you go column by column, right to left, and add the numbers digit by digit. 5 plus 4 is 9, so you write the sum of 9 and a carry of 0. 5 plus 5 is 10, so you write a sum of 0 and a carry of 1. This is because in base 10, a single digit can only hold values from 0 through 9. 10 doesn't fit, so it overflows into the next column. That's what a carry represents. And since there are no more digits, we can just bring the carry down. For every pair of digits, we can create a table of all the possible outcomes and use that to decide on the sum and carry. Looking at the table, 5 plus 5 gives 0 for the sum and 1 for the carry, which is exactly what we got in the last example. Now, binary addition works exactly the same way, just with only 4 possible combinations per column. That last case is important. 1 plus 1 overflows, so we write 0 as the sum and a carry of 1. Exactly like carrying in decimal. Let's go over that point once more. 5 plus 5 equals 10, but base 10 has no single digit for 10, so we carry a 1. 1 plus 1 equals 2, but binary has no single digit for 2, so we carry a 1. We can use this new table to add binary numbers column by column, pretty much like before. 1 plus 1 gives us a sum of 0 and a carry of 1, which we write on the next column. Now let's look at how to turn this into a circuit so we can get the computer to do it for us. We have 2 inputs, A and B, and we need 2 outputs, a sum bit and a carry bit. Notice how the sum column is exactly what an exclusive OR gate produces, and the carry column is exactly what an AND gate produces. I won't go into it too much, but the XOR gate and the AND gate are logical gates. Logical gates take in input bits and produce an output bit based on a set of pre-specified rules. Really quickly, I'm going to go over some of the different types of gates we're going to encounter. The XOR gate only outputs 1 if both bits are different. The AND gate outputs 1 if all inputs are 1. The OR gate outputs 1 if any of the inputs are 1. The NAND gate is the opposite of the AND gate, and it outputs 1 for all cases, except when all inputs are 1. One last thing, logic gates also aren't bound to just 2 inputs. Using whatever their underlying rule is, you can make them have any length. For example, this 4-bit AND gate will be on when all of its 4 inputs are on, and this 4-bit OR gate will be on when any of its 4 inputs are on. So a half adder is simply one XOR gate for the sum and one AND gate for the carry. That's it. Now, you might be asking, why is it called a half adder? Well, that's because it can only handle 2 inputs. It has no way to accept a carry coming in from a previous column. To better see this, let's look at another example. 395 plus 274. 5 plus 4 gives us a sum of 9 and a carry of 0. That's fine. 9 plus 7, however, gives us a sum of 6 and a carry of 1. Now, if we do the next column, you'll notice that nothing in our table tells us what to do when we have 3 numbers. It should tell us how to handle 3 inputs, but it doesn't. To add complicated multi-bit numbers, we need to expand our table. And for binary numbers, here, C in and C out stands for carry in and carry out respectively. Carry out still has the same meaning as the good old carry from before, and carry in is just the carry coming in from the previous computation. The sum is 1 whenever an odd number of inputs are 1. The carry out is 1 whenever at least 2 of the 3 inputs are 1. You should note that the completed full adder is capable of independently processing addition for a single digits place. Now, using a blueprint I found online, we can create a full adder. Testing all the cases, we can verify that it matches the table exactly. The full adder can perform addition for 1 digit. To add larger binary numbers that have a lot more than just 1 digit, we can chain multiple full adders. This is called the ripple carry adder. To create a 4-bit ripple carry adder, we have to take in 4 full adders, again 1 for each digit. Then we wire them up so that each carry out is fed into the carry in of the first bit. Each full adder computes its sum bit and passes its carry to the next stage. The carry ripples from the smallest digit all the way to the biggest digit, hence the name. This works perfectly. It's correct, it's simple, but it has a serious problem. To see this problem more clearly, let's hop into Minecraft. For our purposes, Minecraft is another simulation tool which we can use to make our adder. Here I've got a full adder in a chain of 16. Therefore, this adder is capable of adding 2 16-bit numbers. In the worst case, say, all 1s plus 1, the carry starting at bit 0 ripples all the way through every single stage before bit 15 can compute its final sum. Every extra bit you add makes the adder slower. For 64-bit numbers, the adder will have 64 levels of delay. Modern 64-bit CPUs utilize their internal adders very often. Therefore, the ripple carry adder would be far too slow to do anything productive. We need something more efficient. The fundamental bottleneck is waiting for all the carries to be processed. If we could somehow create some sort of circuit that could process all the carries immediately, we would see a dramatic speed up. This is the key insight behind the carry look-ahead adder. For each bit position I, let's define 2 signals based only on 2 input bits, AI and BI. Before we even know the carry in, we're going to create 2 other bits. The generate bit will generate a carry out regardless of any carry coming in. This is just a simple AND gate between the 2 bits A and B. We're also going to define a propagate bit, which will propagate a carry in to a carry out if 1 arrives. This happens exactly when one of A or B is 1. In other words, the propagate signal is equal to A XOR B. Think of it this way, a position either sparks a new carry from nothing, which is the generate, passes a carry through if 1 arrives, which is the propagate, or kills any incoming carry, which is neither. These signals, G and P, can be computed for every bit position simultaneously and immediately. They depend only on the input bits, not on any carry. Now, here's the magic. We can express each carry out purely in terms of G, P, and the original carry coming in. By definition, our carry generation machine will compute carries like this. Just to clarify on some notation, multiplication is the AND gate and addition is an OR gate. Now expanding the terms, we get this. Notice this, C4 is not waiting on the result of any previous carry. Also notice how C4 can be computed with 1 AND layer and 1 OR layer. Now, none of our carries are waiting on a previous carry and all of our carries are computed simultaneously. CLA is dramatically faster than a ripple carry adder, but look at the equation for C4. It has 5 terms, each getting wider. For a 32-bit adder, C32 would have 33 terms. The AND gates feeding the OR gate would need 33 inputs each. In the real world, very wide gates become impractically slow and expensive. What if we could somehow get rid of the very large gates? How could we create a true CLA adder that would be fast as physically possible? The Kogge-Stone adder is our answer. It is the theoretically fastest adder. It computes all carry signals in O log base 2 of n time, which is the absolute minimum possible for an n-bit adder. It is the most common design for high-performance adders in modern processors. In the Kogge-Stone adder, we still use the generate and propagate signals, but the Kogge-Stone adder cleverly compacts the generate and propagate operations so that we don't have to deal with very large gates. The Kogge-Stone does this with a sequence of stages, each one doubling the span size. In stage 0, we would compute the 1-bit GNP for every position from the raw inputs. This is done simultaneously for all n bits. In stage 1, we combine adjacent pairs. Now every bit has a GP pair summarizing its span of 2 bits. In stage 2, we combine spans 2 bits apart. Now every bit has a GP pair that summarizes 4 bits. For larger adders, this process would go on even further. After log base 2 event stages, every bit position has a GP pair that summarizes the entire span from position 0 up to that position, which is exactly the carry in for that bit. At this point, all the carries are known. Now, all of this might seem like magic, but if we actually compare the math for one of the carries to how we were computing carries in the CLA adder, you can see how they are both identical. The reason for this abstraction is that we now avoid the wide gate problem entirely. At each stage, every node combines exactly 2 inputs. No gate ever needs more than 2 inputs. This keeps gate delay constant at every level. The only con to the Kogge-Stone adder is wiring. Each stage connects nodes that are further and further apart. In stage n of this adder, every node connects to a node 2 to the power of n-1 positions away. For a 64-bit adder, this creates a lot of long wires crossing the chip, which can limit speed in practice due to wire delay. But for most modern processor designs, it's still faster than any alternative. Now that we've got all the theory out of the way, let's hop into Minecraft to actually prove the Kogge-Stone adder is faster. First off, I've got an 8-bit RCA here which we are going to use as a reference. As you can see, it took 8.4 seconds. In the real world, even the RCA would complete in a fraction of a second. I've just slowed down the simulation here so the difference is easier to see. Next up, we have the new contender, the Kogge-Stone adder. Now, credit where credit is due, I did not make this on my own. I found the model from an old 2012 Minecraft video. As you can see, the wiring is a lot worse than before, even though this is only an 8-bit Kogge-Stone adder. A 64-bit version, as you can imagine, would have been an absolute nightmare. Finally, if we run it, you could see that it only takes 4.5 seconds. A clear winner. Now, the difference may not seem as big as all the new complexity, but if we were to run the 64-bit versions for both, the difference would grow to be a lot more.